Assalamualaikum and a very good day to my panel. My name is Nur Ain binti Arifin. Today I would like to present about my final year project presentation. The title of my final year project is Thermo-Hydraulic-Electrical Analysis of Hybrid Nanofluid Aluminium Oxide Silicon Dioxide Water in Pemfc Charge Channel. I am under supervision of IR Dr. Ini Azin Zakaria. For the introduction, proton exchange membrane fuel cell, also known as Pemfc, is one type of fuel cell that generates electricity to electrochemical reaction between hydrogen and oxygen. The Pemfc produces heat and water as byproducts. Pemfc is one of the greener options to the fossil fuels since the emission is almost negligible. Pemfc can be used in all applications such as automotive, industrial, and aircraft. Nanofluid is nanoparticles suspended in base fluids such as water, ethylene glycol, bioglycol, and etc. The nanoparticles can be categorized into four main groups. There are metal-based, metal oxide-based, carbon-based, and hybrid or mixed metal-based. The advantage of using nanofluids in Pemfc is that it is one of an alternative way of cooling method without sacrificing the radiator size in Pemfc. This research is about the effect of heat transfer, pressure drop, and electric current drop by hybrid nanofluids aluminum oxide silicon dioxide in water in Pemfc charge channel. The objective for my research is that first to study the effect of hybrid nanofluids in terms of heat transfer and pressure drop in charge channel of Pemfc. And second, to investigate the electric current drop in charge channel of Pemfc due to nanofluids. For the scope of study, I study about four main things, which are first proton exchange membrane fuel cell, which also known as Pemfc. To be specific, is charge channel. Second, nanofluids, aluminum oxide, silicon dioxide, and water. And third is Reynolds number from 300 to 700. And the last one is heat transfer, pressure drop, and electric current drop. For the methodology part, how to calculate the aluminum oxide and silicon dioxide needed is by using these two formulas. The Phi symbol represents the volume concentration percentage, and 0.5% volume concentration is required for my research study. After that, these nanoparticles is added with base fluid, which is water, and stir using the magnetic plate stirrer. The duration required for both nanofluids are different, which are 20 minutes for aluminum oxide and 10 minutes for silicon dioxide. For sonication process, the duration is 3 hours for both nanofluids. This is to increase the stability of the nanofluids. And this process, both process are called two-step method. For the project finding of my research, first is the channel temperature. As Reynolds number increase, the channel temperature decrease. This is to show that the lower the channel temperature, the better the heat transfer of the fluid. This is related to the thermal conductivity of the fluid. Higher thermal conductivity will result in higher Brownian motion movement that will improve the heat transfer behavior of the fluid. The next is heat transfer coefficient. As the Reynolds number increase, the heat transfer coefficient increase. The heat transfer coefficient define the convective heat transfer ability of a moving fluid. The higher the value of convective heat transfer coefficient, show better heat transfer capability. Based on the figure, based on the diagram, the highest transfer coefficient was 0.5 volume concentration of aluminum oxide at Reynolds number 700. which was about 43.12% higher than the base fluid. The next one is Nusselt number. This trend also same as before. As the Reynolds number increase, the Nusselt number also increase. This is because the Nusselt number is calculated from the convective heat transfer. And for the pressure drop, as the Reynolds number increase, the pressure drop also increase. The highest pressure drop was recorded at 1090 hybrid nanofluids, which was 7.266 Pascal, which is equivalent to 63.71% increment as compared to the base fluid. The pressure drop increased due to its viscosity and density of the fluid. The next is pumping power. Pumping power is related to the pressure drop as the higher pumping power, higher pressure drop requires higher pumping power due to viscosity and density. The higher pumping power needed to flow the fluid in a high speed. Lastly, for the current drop, as Reynolds number increase, the current drop also increase. The highest current drop was recorded at aluminium oxide singles nanofluid, which is at Reynolds 700. This is due to aluminium oxide has higher thermal conductivity compared to the other fluids. I think that's all from me. Thank you. And if you have any inquiries, please contact me at my phone and email number stated at this slide. Thank you.